So lots of other batteries out there, and one common battery that was around a few years ago were nickel-cadmium batteries. It's the sort of thing you find in old electric power tools and things like that. It has a higher energy density than lead acid, but it is not as tolerant as lead acid of charge regime. I've been sort of laying the law down about lead acid, but one of the nice things about lead acid, if you've got a variable input, it will take it and it won't be too upset about it. Whereas devices like nickel cadmium are a bit more sensitive to that sort of variable charge regime that you might get off of a renewable generator. They have a relatively high self-discharge. They've often been used in UPSs for computer power systems as well. One of the nasty things about nickel cadmium is it has a memory effect. And what a memory effect is if you charge and discharge it to, say, 20% depth of discharge, you then think, oh, okay, I need to go away and I can't, and you try and take out more out of it, you find it won't go. It gets stuck in the cycle that it's been working in. And you would often find that with these power tools, you know, people leaving them on charge all the time, and then but it's been on charge all the time and it's giving me nothing. And it basically, you're not getting the full charge out of the battery because of the memory effect. The internal resistance drops with temperature, so that's maybe a good thing. So probably not better in a colder climate. The nasty thing about nickel cadmium is disposal. Cadmium is highly toxic, and so there are more disposal issues. One of the great things about lead acid is that it's almost 100% recyclable, and is, you know, if you're buying a lead acid battery in Europe, then it will go to a recycler and that lead will land up back in a new battery in due course. In developing countries, of course, disposal systems may not be quite so prevalent, but lead does tend to have value, and but it tends to get recycled. The recycle rates in lead acid batteries are incredibly high. It's well over 99%.
Is there a way of like changing the memory effect once it starts?
I haven't heard of, but there are various people who sort of used to sell smart chargers, which were supposed to do some pulse charging, which was supposed to get rid of it. Whenever I've tried to do that, it's never worked. I've always tended to steer clear of nickel cadmium just because of the disposal issue. It becomes no one wants to take it. You basically have to pay for someone to dispose of it.
We used to put them on a slow deep discharge.
Yeah.
And try to get you to turn the memory on that to
Discharge
it right down the bottom. And some people tried putting them in the freezer overnight.
Did that do any good?
I never tried that.
Yeah.
I know we used to do deep discharge.
Yeah, and the risk with deep discharge nickel cadmium batteries, it can internally short as well. That can be as bad for it as leaving it permanently on charge as well. They really like to do a bit of work. Nickel metal hydride came along probably about 15 years ago. Has less memory effect and a higher storage capacity than nickel cadmium for bottom, but it does have a relatively high self-discharge. So you don't mind too much if it's just, you know, in your torch or your radio where you just plug it in and charge it up again. But again, for longer term storage, it's maybe not so good. It was used in the early hybrid and electric vehicles, probably being moved over to lithium ion now, but it's less toxic than nickel cadmium as well. And then we come to the smart kid on the block, lithium ion, which is really where a lot of the interest is at the moment. And the interest there is because it has it has a high energy to weight ratio, and it can show some really good charge discharge efficiencies, 86 to 96%, depending on the technology that you're using. You need to be very careful. This charge discharge efficiency is basically, if I put in 100 ampere hours, do I get 100 out or do I get 50 out? You know, so it's what's your cycle efficiency. Typically for lead acid, it might be something in the order of 70 to 80%. you're into what you get out. Whereas some of these lithium ions are sort of 86 to 96%. But remember, on top of that, you've got any conversions that you have to do. So if you want that lithium ion to run an inverter, then that loss goes on top of that efficiency. So you might be losing another 5 or 6% that way. One of the reasons that lithium ion is so good is the cell voltage is higher. The higher the cell voltage you can get, the more storage you get. Because basically, if you've got 100 ampere hours at 2 volts, you can double that to 100 ampere hours at 4 volts. That's twice the amount of capacity. So higher cell voltages tend to be a good thing. Lithium is also good because it's an extremely light element. And so we're finding them in all sorts of things like our mobile phones. The energy density is also a bit of an issue. There was the thing about Samsung phones bursting into flames. Well, because you've got all that energy packed into a small space, if that battery starts to get out of control, it can deliver a lot of current for a very short period of time. And that's at that point that your phone starts going horribly wrong. So you need to have management systems on these lithium batteries to a much greater extent than you do on, say, something like a lead acid battery. The capacity degrades with shelf life. This is an issue for the electric car vehicle, which is where your recycling's coming in. So they're saying, so all of a sudden, you said my Jaguar XI, whatever it is, will go 200 miles. 3 years later, it's only going 150 miles. You're not a very happy customer. So they say, no, okay, what we'll do is we'll change it out. You get a brand new shine, and now they're recycling that battery off to someone who's maybe not quite so fussy. Most of the drive in these technologies coming from the automotive industry. So you may have heard of Tesla building a huge 100 megawatt battery in Australia. That's basically using the same battery as they're using in their electric vehicles. So they develop it for their electric vehicles, and then it's moving into the static battery market. And they need to be stored in a charged state. So they don't want to be left off charge for long periods of time. They work in a very different way to lead acid batteries, in as much that they are about an ion exchange. And we talk about lithium ion as a battery, but in actual fact, it's a whole raft of different kinds of battery. And the things that change in the battery are the makeup of this cathode. That's the positive connection to the battery. Typically, the anode, the negative connection, is graphite. But this cathode is typically, it can be a whole range of different materials, all of which are basically lithium oxides, but then they've usually got other stuff added to them. So in this particular case, it's got some manganese in it. So and unlike the lead acid battery, which is basically an electron exchange device, the lithium ion battery is an ion change device, and it's the movement of ions through a membrane that dictates how it works. So these are the lithium ions which are embedded inside the cathode, and then they migrate onto the anode, and so you're discharging at that point, or they can migrate back again depending on whether you're charging or not. The battery can be designed either for a higher energy density, so more energy in a smaller space, but then they tend to be less thermally stable, or they can have a lower density and more stability. And the chemistry within the battery affects the charge and discharge rates. The amount of capacity of the battery, I've got another slide of that, is dictated by the amount of electrolyte that there is in the battery. So the amount we have here dictates how much charge you can store in the battery. So if you have a battery where there's not very much, these two plates are effectively very close together, then that means that you can get lots of power out of that battery because you haven't got very much internal resistance, but you get less capacity. Or you can move them apart, you get more capacity, but you can get less power out. The problem for the electric car makers is they want both. They want mileage, which is capacity, but they also want power because we all like to drive fast. They don't want a vehicle that's going to be sluggish, so they want to get lots of power out of it. So what they have to do is they have to over-design the battery so it can do both things. So we can split the lithium-ion cells into these sort of two classes. There's the high power and the high energy, and they all have different charge and discharge characteristics. They all have to be charged at the correct voltage, and they don't tolerate overcharging. Well, the nice things about lead acid, if you overcharge it, it's not a great thing to do to a lead acid battery, but all it will do is just do a bit of off-gassing. If you overcharge a lithium-ion battery, then you're into a whole world of woe. Everything from it exploding to bursting into flames. And so that means that there has to be much better charge control of the battery, especially if you're using a renewable energy source, which is jumping up and down all over the place as the clouds go across the sun.